Hello, everybody. This is the Zoom meeting for Chapter 3. Problem solving. All right, so 3-1. Calculating average and instantaneous velocity. 3-1, we are a robotic vehicle, or rover, is exploring the surface of Mars. The stationary Mars lander is the origin of coordinates, pardon me, and the surrounding Martian surface lies in the XY plane. The rover, which we represent as a point, has X and Y coordinates that vary with time, and they are as follows. X equals 2 meters, 2.0 meters, minus a 0.25 meters per second squared, times t squared. That's x. Y equals 1 meter per second times t, 1.0 meter per second times t, plus 0.0025 meter per second cubed times t cubed. All right, so those are our x and y coordinates. And we are supposed to find the rover's coordinates and distance from the ladder at t equals 2 seconds. That's A. And then B, we are to find the rover's displacement and average velocity for the interval t equals 0 to t equals 2 seconds. C, find a general expression for the rover's instantaneous velocity. Express v at t equals 2 seconds in component form and in terms of magnitude and direction. All right, let's begin. So for A, we are to find the rover's coordinate and distance from the ladder at t equals 2 seconds. I'm going to simply put in t equals 2 seconds. So x is going to be 2.0 meters minus 0.25 meters per second squared. Is that t squared? Let's see. Must be t squared. Yeah, I made a mistake here. That's t squared there. Times 2 seconds quantity squared. And that's going to give me, let's see, I'll just go with the book that says 1.0 meter. And y is going to equal 1.0 meters per second times 2 seconds plus 0.0025 meters per second cubed times 2 seconds quantity cubed. So, and this one, the value there is going to be 2.2 meters. So this is my x coordinate right here, and that's my y coordinate. Now to find the distance, I'm just going to simply take the square root of the sum of the squares. R equals the square root of x squared plus y squared equals the square root of 1.0 meter squared, quantity squared, plus 2.2 meter quantity squared. And the value there is going to be, the distance is going to be 2.4 meters from the rover. Okay, part B says, pardon me, find the rover's displacement and average velocity vectors for the interval t equals 0 to t equals 2 seconds. All right, for the velocity, for the displacement vector, let's see. It's going to be r equals xi plus yj. So let's do that. Oh, pardon me. There we go. We've got equals 2.0 meters minus 0.25 meters per second squared times t squared, and that's going to be I, plus 1.0 meter per second times t, plus 0.0025 meters per second cubed times t cubed j. All right, what else are we supposed to do here? That's the displacement vector, and now we need to find from the interval t equals 0 to t equals 2. Okay, so for t equals 0, I'm just gonna, so r t equals 0. I do enter the value, and let's see, I get 2.0. 2.0 meters I plus, it's going to give me a 0 there and 0 j. 0 j. For 2, for the displacement vector at t equals 2, let's see, I'm going to put in 2 and I'm going to get 4 times that is going to be, so that's going to be 1 meter I plus, it's going to be 2, oh, let's see what the book has. For, let's see, yeah, that's going to be 2.2 meters j. 2.2 meters j. All right, for the velocity vector, average velocity, v average, is simply delta r over delta t. So let me get some space here. All right, so we were on 3.1b. Delta r over delta t is going to give me r2 minus r1 over t2 minus t1. So r2 is going to be, this is going to be, let me erase some of this. Let's see. 1.0 meter I plus 2.2 meter j, and then minus 2.0 meter I plus 0.0 j. And this is delta r. And let's see what that's going to give me. That's going to give me -1 meter, -1.0 meter I plus 2.2 meter j. And then that will be over 2 seconds minus 0 seconds. So my V average is going to be delta R over delta T. And finally, dividing through, we're going to get -0.5 meters I per second, meters per second, plus 1.1 meters per second J. That's part B. Okay, 3.1, part C asks us to find a general expression for the rover's instantaneous velocity vector v. Express v at t equals 2 seconds in component terms and in terms of magnitude and direction. Okay, so for our instantaneous velocity, I take the derivative. So let's do that. We have x is going to equal 2.0 meters minus 0.25 meters per second squared, meters per second squared times t squared. And dx dt is going to equal to negative 0.25 meter per second squared times 2 times t. And let's see. D, what was y? Y. 1 point y equals 1.0 meters per second times t plus 0.0025 meters per second cubed times t cubed. And for y, we're going to get dy dt equals 1.0 meters per second plus 0.0025 meters per second cubed times 3 times t squared. I'm going to go ahead and finish. This is going to be a negative 0.50 meters per second t, and this guy is going to be 1.0 meters per second plus 0.0075 meters per second cubed times t squared. So now to write this, my velocity vector is going to be equal to v sub xi plus v sub yj, and that's going to be equal to negative 0.5 meter per second t. This is going to be I plus the bottom one plus 1.0 meter per second plus 0.0075 meter per second cubed t squared j. All right, part C, this part I'm supposed to express, let's see, express v at t equals 2 in component forms and in terms of magnitude and direction. So in component forms, I took dx dt and dy dt and entered the value 2 seconds here. And for my x component, my v sub x, I get negative 1 meter per second. For my v sub y, I get 1.3 meters per second. Now, to express that in vector form, let's get the magnitude in polar coordinates. So I'm going to get r, or just v sub v at 2 seconds equals the square root of negative 1.0 meters per second squared plus 1.3 meters per second squared. And that value is going to be 1.6 meter per second. This is my magnitude. And for my direction, I'm going to take tangent theta equals y over x. Tangent inverse of y over x is going to give me theta. So tan inverse of 1.3 meters per second over negative 1.0 meters per second is going to give me negative 52 degrees. So that's my direction, and that's my velocity magnitude at t equals 2. Okay, example 3.2 says, let's return to the motions of the Mars rover in 3.1. So we're going to use that problem, all the values we had in there. Find the components of the average acceleration for the interval t equals 0 to t equals 2 seconds. Okay. Find the instantaneous acceleration at t equals 2 seconds. So let's see, we had v sub x and v sub y, and those were for the instantaneous velocity dx dt and dy dt. And our values or our expressions were negative 0.25 meters per second squared times second squared. Let's see, times 2t, and that was going to equal negative 0.5 meters per second squared times t. And this guy was, just cut to the chase, it was 1.0 meters per second. And that was plus 0.0075 meters per second cubed times t squared. All right, so find the components of the average acceleration for the interval t equals 0 to t equals 2. So I'm going to find the components for t equals 2. Let's see, v sub x at 2 is going to be 0.05 meters per second times 2 seconds. Go ahead and do that, negative 0.5 meters per second times 2 seconds, and that'll be negative 1. Let's see, is that negative 1? That's meters per second squared, sorry. Negative 1 meters per second. And v sub y at 2 is going to be equal to 1 meter per second, 1.0 meter per second plus 0.0075 meters per second cubed times 2 seconds squared, 2 seconds squared, and let me just get this value from the book. 1.3 meters per second. 1.3 meters per second. And v sub x at 0 is going to be, let's see, put in a 0, that'll be, let's see, 0.5 times 0 seconds is 0. 0 meters per second. And v sub y at 0, 1 minute. Okay, everybody, sorry, that was my mommy. And now I've kind of lost my place. But no, I'm back to finding the y component of velocity at t equals 0. So let's see, the y component at t equals 0 is going to be 1 meter per second, right? Yeah, 1 meter per second. 1 meter per second. All right. Now I need to find the average acceleration during that interval. So let me get myself some space here. A average is going to be equal to delta V over delta T. And we have two components here. So let's do the delta Vx and over delta T is going to be equal to V2 minus V1 over T2 minus T1. We put that in. All right, be correct about that. Oh, that's not a vector. That's just the components. Let me be really correct about it. Erase that. Erase. Yeah. Okay. So we have, let's see, negative, let's see, v -1 meter per second minus 0 meter per second over 2 seconds minus 0 seconds. And that's going to give me negative 0.5 meters per second squared. Negative 0.5 meters per second squared. For my A sub X average, for my A sub Y average, I'll do the same procedure and I'm going to get 1.3 meter per second minus 1.0 meter per second. Over 2 seconds minus 0 seconds. And that's going to give me a 0.15 meters per second squared. Now I'm supposed to express that in vector form. Okay, do that now. Am I supposed to express it in vector form? Using, let's see. All right, so I was not supposed to express it in vector form. I'm supposed to be finding instantaneous acceleration at t equals 2 seconds. So A is going to be equal to the derivative of dv dt. So what do we have here? We have A equals dv dt, and we have for x we have negative 0.50 meters per second squared, and then I plus, and I have 0.0075 meters per second cubed times t squared, so that would be 0.0075 meters per second cubed times 2t, which would be 0.050 meters per, this is J, second squared I plus 0.1, is that 0? Oh, there's only 1 0 there. 0.15 meters per second cubed times TJ. Okay, and then now to solve for that instantaneous acceleration at t equals 2. All right, so at t equals 2, this is my x component is going to be a sub x at t equals 2 is going to be negative 0.5 meters per second squared. And a sub y at t equals 2 is going to be, let's see, put in 2, 0.30 meters per second squared. Now, to find the magnitude and direction, I'll do it just in the same manner that I found the magnitude and direction of the velocity in the other. So A equals the square root of negative 0.5 meters per second squared, quantity squared, plus 0.30 meters per second squared, quantity squared. And that's going to give me 0.58. The magnitude equals 0.58 meters per second squared, 0.58 meters per second squared. To find the direction, I'll take the inverse tangent of y over x. So tan inverse of 0.30 meters per second squared divided by negative 0.5 meter per second squared is going to give me a negative 31 degrees. All right. I needed to finish that example 3-2. I had, let's see, I had a negative x component and a positive y component. So my acceleration vector is going to be here with the x component of, let's see, negative 0.5, negative 0.5, and my y component is y component, let's see, 0.3, 0.3, and this angle is going to be 31. So this angle right here is 180 minus 31 equals 149. All right, so we'll use that angle. Okay, example 3.3 states, for the rover in examples 3.1 and 3.2, find the parallel and perpendicular components of acceleration at t equals 2 seconds. Okay, so what we're going to do is we're going to find the components of the acceleration vector that are perpendicular and parallel to that of the velocity vector. All right, so what we need to know is the angle between the two vectors and the magnitude of the acceleration vector. All right, so let's see. From example 3.2, the particle has an acceleration. We know the magnitude, A, equals 0.58 meters per second squared, 0.58 meters per second squared. And we knew it was in the third quadrant. It had a angle of negative 31, so this is going to be 31. So this is going to be what? 180 minus 31, 149. And the velocity vector, it had an angle of 128. So maybe somewhere here, 128. So 149 minus 128 is going to give me 121. Okay, so the angle between them, this is A and this is V, is 21. So this is pretty simple. So we get a, let's see, A perpendicular is going to be this guy, this sine, and A parallel is going to be there. So A parallel is going to be 0.58 meters per second squared times cos 21. And A perpendicular is going to be 0.58 meters per second squared times sine of 21. And what are those values? A parallel is going to be 0.54 meters per second squared, and A perpendicular is going to be 0.21 meter per second squared. Okay, that's example 3.1. I think that's all. Wait. Yes. Problem 3-4 states that a skier moves along a ski jump ramp. The ramp is straight from point A to C and curved from C onward. The skier speeds up as she moves downhill from point A to point E. Here her speed is a maximum. She slows down after passing point E. Draw the direction of the acceleration vector at each of the points B, D, and E. So at B, it's straight down. At D, she's got a component going towards the center of the circle, centripetal component. So she's got a component this way and a component that way. So we're going to meet in the happy median here. At E, it's no longer downhill. She only has a component up. And at F, she's got a component this way and a component this way. So we're going to go with that. All right, that was 3-4. Example 3.5 states, let's consider again the sphere in conceptual example 3.4. What is her acceleration at each of the points G, H, and I after she flies off the ramp? So now she's here. She's got a G, H, and I. And in this example, her acceleration is always due to gravity and it points straight down. So that's her acceleration. Let's see, the skier's acceleration changes from point to point, but as soon as she leaves the ramp, she becomes a projectile. So she's jumping here. So it points G, H, and I, and indeed at all points after she leaves the ramp, the skier's acceleration points vertically downward and has a magnitude of G. Okay, example 3.6, a body projected horizontally. In this example, we have a motorcycle riding off the edge of the cliff. Just at the edge of the cliff is magnitude of 9 meters per second. So at the edge of the cliff, here's the cliff. The guy's riding like this. And he's got a horizontal velocity, v sub x equals 9 meters per second. That's the only component. Find the motorcycle's position, distance from the edge of the cliff, and velocity 0.5 seconds after it leaves the cliff. Okay, so for position, we're going to find the x and the y coordinates. So we have this guy we're having a projectile problem. And in this projectile problem, in any projectile problem, it's convenient to separate it into its x and y components. So we'll use our displacement equation. So x sub x equals, we'll call this 0. That's, well, the displacement equation, recall, is x final equals x initial plus v naught t plus 1/2 at squared. And we'll call the edge of the cliff 0. So this guy will be 0. And v naught is going to be 9 meters per second times t. That's and I have no acceleration in that direction. And my position in the y direction is going to be 0 once again. I have no initial velocity in the y direction. It's going to be 1/2 times a negative 9.8 meter per second squared times t. And my time was 0.5 seconds. So for my x sub x is 9 meters per second times 0.5 seconds. That's going to be 4.5 meters. And for my x sub y, it's going to be 1/2 times a negative 9.8 meters per second squared times 0.5 seconds. And that's going to give me a negative 1.2 meters. All right, so that's my position at that time. Okay, to find my distance from the edge of the cliff, I will simply take the square root of the sum of the squares to find r. Okay, so r is going to equal to the square root of x squared plus y squared, and that's going to be equal to the square root of 4.5 meters quantity squared plus a negative 1.2 meters squared, and that will give me a 4.7 meters from the edge of the cliff here. All right, now what do I have to do? Find the velocity components at t equals 0.5 seconds. Is that what I'm supposed to find? And all right. So let me clear all this. So let's see. Recall that our velocity equation is v final equals v initial plus acceleration times time. So my v sub x is going to equal to 9.0 meters per second. I have no acceleration in that x direction. And my v sub y is going to equal to 0 plus a negative 9.8 meters per second squared times, was that 0.5 seconds? Yeah. 0.5 seconds, and that's going to be equal to a negative 4.9 meters per second. All right, those are my components. And find, let's see, to express that in vector time, or vector v equals 9.0 meters per second. I minus 4.9 meters per second. J. All right. I'm supposed to find my magnitude and direction now. For my magnitude, v is going to equal to the square root of v sub x squared plus v sub y squared equals the square root of 9.0 meters per second quantity squared plus a negative 4.9 meters per second quantity squared. And that's going to equal to 10.2 meters per second. And to find my angle, I'll use tangent inverse of negative 4.9 meters per second divided by a 9.0 meters per second. And that's going to give me 24.4 meters per second. Let's see, 24.4. Oh, no, wait. Negative 29 equals a negative 29. Example 3.7, height and range of a projectile, a batted baseball. This time we will have an initial y component. So we have a batter as a baseball so that it leaves the bat at speed v naught equals 3 meters per second and at angle 53.1 degrees. A, find the position of the ball and its velocity, magnitude and direction, at t equals 2 seconds. And B, find the time when the ball reaches the highest point of its flight and its height, h, at this time. C, find the horizontal range, r, that is the horizontal distance from the starting point to where the ball hits the ground, and the ball's velocity just before it hits. Okay, so what do we have here? We have a ball. It's got a magnitude of 37 meters per second and an angle of 53.1 degrees. All right, the first thing I need to do is find the initial components of velocity. I need to find v naught x and v naught y. And so for v naught x, I'm going to get the magnitude, 37.0 meters per second, times the cosine of the angle, 53.1. And that value is going to be 22.2 meters per second. For the y component, I'll do the same deal, 37.0 meters per second. This time it'll be the sine, this guy, sine of the angle, sine of 53.1, and that's going to equal 29.6 meters per second. And that makes sense. My angle is greater than 45, so my y component is going to be larger than my x component, right? All right, now what do I need to do? Find the position in the ball of the ball and its velocity direction at t equals 2. Okay. So let's see, for position, I'm going to use that displacement x final equals x initial plus v naught t plus 1/2 at squared. All right, for my x component, I have no acceleration in that direction. We're going to always ignore wind resistance here. So we've got x sub x equals, we're calling this guy 0, 0, 0, 0. So this first initial position is 0. And we've got v naught is 22.2 meters per second times t. What is t here? 2 seconds times 2 seconds. That's my x component. And let's see, I get 44.4 meters. 44.4 meters. And for my y component, x sub y, I have, once again, I started 0, and I have initial y velocity of 29.6 meters per second times 2 seconds. Then I have an acceleration in that direction equal to gravity, minus 1/2 or plus 1/2, negative 9.8 meters per second squared times 2 seconds quantity squared, and that's going to give me 39.6. 39.6 meters. Now, let's see, am I supposed to do anything with that? I guess just find the components. Find the position of the ball and its velocity. Okay, so those are my component positions. Am I supposed to do anything with those? No. All right, so let me pause, clean up the board, and continue. Okay, now I need to find my velocity. So let's see, I'm given let me go with those. V naught x, and V naught y. X was, let's see, 22.2. And V naught y was 29.6. All right, so my velocity, V sub x, remember that velocity equation, V final equals V initial plus acceleration times time. All right, so V sub x is going to be equal to 22.2 meters per second. I have no acceleration in that direction. And V sub y is going to be equal to 29.6 meters per second plus a negative 9.8 meters per second squared. And that's 2 seconds, is that correct? Times 2 seconds. And this is going to be equal to 10 meters per second. 10.0 meters per second. All right. So now my total velocity, the magnitude of it is going to be equal to the square root of its components, squared. So this is going to be 22.2 meters per second, quantity squared, plus 10 meters per second, quantity squared. And that's going to give me 24.4 meters per second. I need a direction. So theta is going to be equal to tangent inverse of y over x, 10 meters per second over 22.2 meters per second. And that's going to be equal to 24.2 degrees. All right, that's my velocity. We just did the position, we did the velocity. All right, pause, clean up the board. All right, my next challenge is to find the time when the ball reaches its highest point. Now, to do this, I've got to consider the y component. Why do I have to do that? Because the value of that velocity of the y component when the ball reaches its apex is going to be 0. So this will be pretty simple to solve. I've got v final equals v initial plus acceleration times time. So I'm going to use 0 equals, what was my initial velocity in that direction? Let's see, 29.6 meters per second plus a negative 9.8 meters per second squared times time. All right, so now I'm going to rearrange it and put negative 29.6 meters per second divided by a negative 9.8 meters per second squared is going to give me t, and t will equal, let's see, 3.02 seconds. 3.02 seconds. And this value right here, by the way, is going to be half the time. Oops, let me pause. I guess I'm supposed to find my height at that time. So I'm going to once again use my y component to do that. So I'm going to use my equation, my displacement, x final equals x initial plus v naught t plus 1/2 at squared. And I'm going to solve for that position at t equals 0.32. So I'm going to have x final equals 0. Remember, we determined it started at 0, 0, my coordinates, plus, what was that initial? 29.6 meters per second times 3.02 seconds plus a 1/2, bless me, times a negative 9.8 meters per second squared times 3.02 seconds quantity squared. And let's see, what do I get there? I get 44.7 meters. So max height, equals 44.7 meters. All right. Okay, I'm going to clear all this. Now I am going to find the range. The range is the distance that the ball travels. And your book does it by finding the total time by using the displacement for the, we know that it goes like this. We know it's a level playing field. So your book does it by using the y displacement as being 0. I'm going to do a little shortcut. And since I know it's a level playing field, and I know this is 3.02 seconds, 3.02 or 3.2? Yeah, 3.02. I'm going to assume it's got a symmetric path, and I'm going to use my total time equals 6.04 seconds. Anyway, so I'm going to use my displacement equation. Once again, x final equals x initial plus v naught t plus 1/2 at squared. And this time I want the range. The range is this guy, the total distance traveled in the x direction. So I'm going to use my x component. So I'm going to have x final equals 0 plus, what was my original, 22.2 meters per second, times 6.04 seconds. And we have no acceleration in that direction, so this is going to be 29.6 meters. And that's my range. If we had some kind of vertical displacement, we would solve it in a different manner. We would solve for t in a different manner. I recommend you guys watching my projectile videos. They go into very much depth on this subject.